Hello everyone, my name is Peng Peng. I'm from Hunan University. In this presentation, I will give a talk about my paper, MPC, Minimal Property Cut RDF Graph Partitioning. This is a paper co-authored with Tamer Zhou from University of Waterloo, Lei Zhou from Peking University, and two my students, Chen Yan and Chen Junliu. Okay, let's begin the presentation. This is the outline of my presentation. First, let me briefly introduce the background of distributed RDF data management. RDF is the abbreviation of Resource Description Framework and is a data model widely used for knowledge bases. In RDF model, everything can be represented as a resource. Each resource can have some properties and property values, and the two resources can be connected by a named relationship. For example, the right-hand figure shows a resource of India actor Zayed Khan, and he has relevant properties and resource. An RDF dataset can also be seen as a graph with resources and literal vertices, and the relations between them are edges with labels. For example, the following figure is an RDF graph. It's collected from DBpedia and describes some resources of India actors. On the other hand, SPARQL is a structured query language designed for querying an RDF graph. A SPARQL query can also be seen as a query graph with variable. The following figure shows an example SPARQL query and its query graph. Then, answering a SPARQL query equals to finding subgraph homomorphism matches of the query graph over the RDF graph. As more and more people publish their datasets in the RDF model, the current size of RDF datasets has become larger and larger. For example, the RDF dataset Yago, built by Max Planck, has nearly 284 million tuples. Freebase, now owned by Google, has about 2.4 billion tuples. DBpedia, the most famous RDF dataset, now has about 9.5 billion tuples. So it's important for us to design a distributed RDF system to manage its large RDF dataset. A typical distributed RDF system architecture is partitioning-based architecture. In this architecture, an RDF graph is partitioned through different sets, and the design objective is to parallelize query persistence with as little interset communication as possible. So in the partitioning-based architecture, the query execution model is to partition the input query in the same way of data partitioning and try to minimize the inter-partition join. In particular, we first decompose the input query into subqueries over partitions. Then we execute each subquery and its relevant sets, and join the results to form the final results. In the partitioning-based architecture, the core problem is how to partition the RDF graph. Existing approaches can be classified into three types. The first type is vertex disjoint, which put each vertex in one partition. Existing vertex disjoint approach used for the partition-based architecture have a problem that they only try to minimize edge cuts rather than minimize the interpartition joins. The second type is edge disjoint, which put each edges in one partition and are widely used in many cloud-based systems. Their objective is to avoid too many scans in the cloud, but not avoid interpartition joins, so they are not designed for partitioning-based architecture. There are also some other partitioning approaches that consider some extra information, such as workload. In this study, we will talk about the data-driven method and don't consider workload. In this study, we propose a vertex disjoint RDF graph partitioning approach named Minimal Property Cut, MPC for short, for avoiding the interpartition joins in distributed SPARQL query evaluation. We prove that the MPC problem is NP complete and propose a greedy heuristic to solve this problem. We define the types of queries and can be independently executed in MPC partitioning, and the set of such query is larger than what is supported by existing approaches. We discuss how a query is decomposed into one of these types for independent execution. Now, let us go deep into the minimal property cut problem. First, let me give some important definitions in this study. Given a vertex disjoint partitioning, a property is called a quotient property if and only if there is at least one quotient edges with that property as its label. Otherwise, it's called an internal property. Note that an edges with a quotient property does not mean that it has to be a quotient edge, but there can many edges with the same properties, but only some of them might be quotient edges. For example, for the example partitioning in the following figure, resistance is a quotient property, but edges from vertex 6 to vertex 4 with the property resistance is not a quotient edge. However, if an edge has an internal property, it must be an internal edge. The important point here is the distinction between quotient edges and quotient property. As discussed before, in the partition-based architecture, the main performance bottleneck is inter-partition joins. Then if all properties in a query are internal, it can be executed independently over each partition without interpartition. If a query can be independently executed without interpartition joint, it can be fully parallelized without any communication cost and has high performance. So we propose a new partitioning approach to maximize the number of internal properties. It may increase edge cuts, but minimize number of unique property cuts. The following figures gives an example for comparing the minimal property cut with the minimal edge cut. The blue dash line indicates an example minimal edge cut partition. In this case, there are three quotient properties, three quotient properties: resistance, birthplace, and producer. Then the example query in the red hand would have a quotient match, so it cannot be executed independently. On the other hand, the red dashed line partition is the result of MPC partition. In this case, although there are four quotient edges, but there is only one quotient property, birthplace. Example queries in the red hand does not contain this property, so it can be executed independently without interpartition join. And so the performance over MPC is much higher than over minimal edge cut partition. The above example shows the motivation of the minimal property cut. Formally, we can define the minimum property cut as the following. We try to partition the RDF graph where the number of quotient properties is minimized and the partitioning is balanced. We can prove that the MPC partitioning problem is NP-complete by reducing the NP-complete minimal edge cut problem to the MPC problem. Then we propose a greedy heuristic algorithm of the following framework for MPC problem. First, we select a set of internal properties. For example, we assume the internal property in the following figures are colored as red. Secondly, each weak connect component of the subgraph induced by these internal properties are quotiented into one supervertex. For example, given the red internal properties, we can quotient the left RDF graph as the red quotient graph. Third, we partitioned the quotient graph using existing vertex disjoint partitioning approach. For example, there are only two supervertices in the example quotient graph, so we can simply partition it into two parts. Last, we uncoarsened the partitioning result of the coarsened graph and get the partitioning result of the original graph. In the above framework of MPC, the core step is how to select the internal properties. Here, we first give the constraint for a property being internal. If a property P is an internal property, any two vertices in a weakly component of this induced graph should be in one partition. For example, as shown in the following figure, if the property first place is an internal property, all the 6 red vertices should be in one partition because all of them are in one weakly connected component of the birthplace induced graph. This means that the birthplace is better not to be an internal property because selecting birthplace as internal can make one partition meet the bound of the set constraint, and any other property cannot be selected as internal. So we can define the cost of selecting internal properties as follows. Given a set of properties, the cost of selecting them as internal property is defined as the size of the largest weakly connected component in the subgraph induced by these internal properties. Now we can give the internal property selection algorithm. First, we initialize an empty set for internal properties and compute the connected component of the induced graphs for each property. Then we iteratively select a property that can minimize the cost of inserting it into the set of internal properties. These steps are repeated until no more property can be selected. To further improve the performance of computing and merging the weakly connected components, we propose to use the disjoint set forest data structure. After we use the MPC to partition the RDF graph in the partitioning-based architecture, we should exclude query in the corresponding way. Here, we first define the independent excludable queries over MPC. Independent excludable query, i.e. for short, are queries that are local to a partition and can be excluded without a join with another partition. There are two types of IE-equals. The first type is an internal IE-equals, which do not contain any quotient property. For example, the right-hand figure, it does not contain the quotient property first place in our running example. So it's obvious that it can be excluded independently and is an internal IE-equal. The second type of IE-equals is extended IE-equals, which are queries that are connected when the quotient property edges are removed. For example, the two queries in the right-hand figure are extended IE-equals. All these two queries can be connected if all quotient property edges are removed. For IE-equals, they can be directly sent to partitions for exclusion, and the results of them at all partitions can be united together as the final results. In real Spark workload, there are likely some queries that are not independently excludable. For these non-IE-equals, we decompose them into a set of IE-equals and join the result. In particular, we first remove quotient properties edges and edges with variables. Then we form some subqueries. Last, we add quotient property edges and edges with variables back to subqueries to get the final decomposition result. The right-hand figure gives an example query decomposition. We first remove the edge with the example quotient property placed and the edges with a variable. Then we form 3 subqueries. Last, we add the removed edge back to the subquery to get the final decomposition result. After query decomposition, the query exclusion model for a non-IE-equal is as follows. When a non-IE-equal is received, it is decomposed into a set of subqueries, and then they are sent to each partition for independent exclusion. The subqueries matches are joined together to get the final results. Now we talk about experiments to verify the proposed MPC partitioning. We do experiments over a lot of RDF graphs, including synthetic and real RDF graphs. Here, we generate two synthetic RDF graphs with 10 billion triples, which are the largest to our norm. We compare our method with three partitioning methods: subject hash, Matisse, and VP. Subject hash randomly pulls each vertex at a partition using a hash function on vertex. Matisse is the well-known minimum edge cut partitioning method, and VP randomly pulls each edges at a partition using a hash function on edge property. We evaluate our experiments on 8 machines running Linux at Alibaba Cloud. We first compared the partition quantity of our MPC and 3-base as shown in the following two tables. Although our MPC partitioning may result in more edges cuts, but always result in the smallest numbers of Poisson property and the largest percentages of I equals. Larger percentages of I equals can result in better performance on both benchmark queries and real query logs. The offline performance experiment shows that our MPC offline performance can tolerate considering the advantage of MPC in online query performance. Last, we evaluate MPC data scalability by varying the RDF graph size from 100 million triples to 10 billion triples in LUVM and WordDial. The results confirm that MPC partitioning is scalable in large RDF graphs. Last, let me give the conclusions. In this study, we propose a new RDF graph partition schemas named minimal property cut, MPC for short, to minimize interpartition join in distributed SPARQL query evaluation. The queries that cannot complete avoid interpartition joins are partitioned into a set of independent executable subqueries. Our experiments show that at least 60% queries are independent executable in MPC on both synthetic and real RDF graph. Okay, that's all. Thank you very much.